Alright, so in the last video we went through this example in the minimum cost network flow problem, and so now we're going to take a look at how to write the minimum cost network flow problem in general. And so let's take a quick look. So this stands for minimum cost network flow problem. Good. So we're going to minimize the sum of our costs times our flows, just like we did before. And for the constraints, what happens? These are the constraints on each node, right? And so this is outflow minus inflow is equal to BI, right? That's how you're getting each of these nodes. And so if we write those down, generally speaking, right, the inflow, or sorry, this is the outflow because it's going from I to J, and then we're summing over all the ones that it's going to. And then this is going from K to I, so this is going towards I, and we're summing across the nodes that it's starting at. Right, so this is outflow minus inflow, and then we'll set that equal to our B sub I. Good. And then finally we just set Xij to be between our upper and lower bounds. Now remember, in the max flow problem, this would be our CE, that would be our capacity, and then this would actually be our flow, and then this would just be 0, right? But I guess I'm getting ahead of myself here. Let's just do the general case first, and then we'll look at the special cases. Okay, good. In the case that we had up here, we didn't have a capacity, right? Or an upper bound. And so in that case, we could just set the upper bounds equal to infinity, and then the lower bounds equal to 0. And finally, we should notice that the problem that we're working with is balanced, right? So that the sum of the BI is equal to 0. Good. All right, so this is the generic minimum cost network flow. Now let's go in and we want to formulate each of our problems, or each of a few of the problems that we've worked with before, as a minimum cost network flow problem. Okay, so the first one will be a transportation problem, and I've already got the transportation tableau set up here, so it's probably easiest just to start with an example so you can kind of see how it works. Because once you see one of them, then the rest of them are pretty much identical. So in this case, I've got two supplies, supply 1 and supply 2, two demands, demand 1 and demand 2. And so over here in my network, I'm going to have supply nodes 1 and 2, and then demand nodes 3 and 4. Okay, and then similarly, we can fill in the rest of these, right? So the costs here are going to be along the edges. So from 1 to 1, or I should say from 1 to 3, this is going to be node 3, and this is node 4. I'll put a note there, 1, 2, oops. Something went flying by the screen there for a second. 2, 3, oops, 3, 4. Oop, I got a Java update. I'm glad that it warned me about that. Okay, so now on my supply nodes, I've got positive BI, so I'm put a positive 4 up here at the top, and a positive 5 here. And then for those are these supplies, right? And then these negative supplies are coming from here and here. Good. And that is how you translate a transportation problem into a network flow problem. And now from the network flow, we can pretty much just do exactly what we did here, right? So we'll just be minimizing our costs subject to our four node constraints. Whoops, gosh, I'm not sure why things are moving around so much here tonight. All right, so let's go ahead and take a look at our minimization problem. We just have the cost from, or the flow from 1 to 3, plus the $2 times the flow from 2 to 4. Oops. Oops, do I have that correct? That was 1 to 4. 2 times 1 to 4. 3 times 2 to 3. Right along here. And then finally 4 times edge from 2 to 4. Good. And then in node 1 here, we just have these two edges here that are moving out, right? And so that corresponds to 1, 3, and 1, 4, and then that equals to our BI value. Similarly, on this node, we just have two outputs. So output, output, and then 5 is our BI value, or in that case, it's our supply value. And then for node 3, all you have are input nodes, right? So those are both going to be negative. And so we have a negative flow, or the negative, we're subtracting the inflow there, and that's going to be equal to our B sub I. And similarly, our last case. Good. So that's how you translate a transportation problem into an MCNFP. Very good. Now the next problem we're going to look at is the assignment problem. And the assignment problem we'll do it very similar, in a similar way, right? We'll first look at our tableau, then we'll translate it into a network, and then we'll translate that into the MCNFP. Good. So here's our assignment problem. We have, in this case, we have 2 people and 2 jobs. And so again, we're thinking of this as like our node 1, node 2, node 3, and node 4, right? And these are going to be our cost values. And so the network is actually going to look identical, right, to the one we just had. 1, 2, 3, 4. And so 1 can assign to 3 or 4, and 2 can assign to 3 or 4, right? And then the cost from 1 to 3 is going to be 2. The cost from 1 to 4 is 5. The cost from 2 to 3 is 3, and the cost from 2 to 4 is 4. Good. Now the question is what do we do about supply and demand nodes? Do you remember how we did that in an assignment problem? Do you remember that it was, we're going to make these supply nodes equal to 1, and the demand nodes equal to, well, we were going to make the demands equal to 1, and so in this case we would make these equal to -1. Good. And so this is now the network flow that we will translate into our minimum cost network flow problem. Good. And so we'll just, it's identical, right? Minimum of x13 2 times x13, right? Plus 5 times x14 plus 3 times x23. Oops. Plus, how many do we have here? 4 times x24. Good. And now node 1. Oops, I keep doing that. Node 1. We have 2 outputs, right? So x13 plus x14, and that will be equal to b1, which is 1. And then the other output one is going to be 2, 3, and 2, 4, right? I keep pressing things that I'm not supposed to be doing here. Okay, there. Now we also have the 2 demand nodes. So for 3, 1, 3, and 2, 4, 1, 3, and 2, 3 will be negative. And then that'll be equal to -1. And then our last one, can you guess? -1, 4, -2, 4 equals -1. Good. And of course our xij's are positive here. Whoops. Good. All right. So in the next video, we'll talk about how to write the shortest path and the maximum flow as a minimum cost network flow problem. See you then.